Now, I will probably say a lot of things that are my opinion and that are probably politically incorrect. Don't take it wrong. It's my opinion that is different from actually most other people's opinions in this kind of context. And when we started doing this, and it was more than 10 years ago, I always have these megalomanous ideas. And everybody was studying their little compounds and maybe a family or so. And I thought, why the hell are we doing this? Why can't we do all compounds? And so we used a different strategy from most people. And our goal was actually to find all possible inorganic compounds that are thermodynamically and dynamically stable. Stoichiometric, ordered compounds. Let's stay within this, so no alloys, no glasses. I mean, alloys and glasses are super interesting, but let's start by solving the first problem that are ordered compounds, stoichiometric. Can we find them all, like Pokemons? And we wanted to do it at the beginning, especially by trying all possible chemical compositions in all possible crystal structures. And then, only then, after we have all compounds, or at least a large selection of compounds, we could scan them for interesting properties that are usually extreme properties, so maxima, minima, or combinations of these things. So most people do the other way around. They search compounds directly for a certain property. Yeah? So this is kind of turning things around. And there's a reason for this. And this may surprise a lot of people, but there are very few possible compounds that you will be able to do in a lab. So the number of possible crystal structures is true, it grows factorially, but who cares, right? The number of stable compounds is relatively small. ICSD has around 50,000 compounds, 10,000 of which are mistakes. Yeah? So talking about experimental data, probably 10 to 20% of these compounds are nonsense. Yeah? There is no other way of putting it. Then, if we could do this is great, because if we know the distribution of a certain property in all compounds, then we can actually find what is extreme. When people came up with giant magnetoresistance, they had no idea what was the scale of possible magnetoresistances. So then they had to go from giant to another superlative. Right? This makes no sense. If you go through the papers, you will see gigantic, enormous, adjectives that have absolutely no meaning because they have never been quantified. For that, you need to know the distribution of properties. We can discuss a million days about this. We will just assume that current theories, DFT, beyond DFT, or whatever you want, are good enough. And our predictions will have a statistical error. And we are aware of our errors. Contrary to what people say, they say, I believe in DFT, I don't believe in DFT. This is not a scientific statement. The statement is the average error of this functional for this property is X. Okay? And then if you know the error, it's a random error. We know what confidence we can have or not in our result and interpret it statistically. Okay, so what do we do? So this is kind of our modern workflow, let's call it like that. It's very simple. After all these years, we have a generative model, similar to the one of Microsoft MatterGen, but better. Above all, much faster than MatterGen. I generate, the computers, around 500,000 crystal structures per day. So this is the rate that we are doing things. We are advancing solid-state physics at the rate of 500,000 new compounds a day. Then this gives us some primitive crystal structure that we optimize with the universal machine learning force field. I will then give you a bit more details of every step. So this is another set of machine learning models that have done spectacular advances in the last 2 years, especially in the last 6 months. I will also show you some numbers. Then from here, we will have a third machine that will predict the distance to the convex hull of stability that gives us a proxy to how synthesizable the compound is. Then we do DFT for what we like. We are doing, then I will show you, we are advancing, we are calculating a bit more than 1 million compounds a year by now in DFT. Then we have a set of other machines to predict properties. based either on this geometry or this one. We have a batch of them, so I will show you some details also. And then if we like it, we may or not do further characterization with DFT, perturbation theory, GW, whatever you want, that are now kind of perfectly easy and accessible methods. So let's go step by step. Let's start with the generative model. There are at least, I would say, 60 or 70 generative models that came up in the literature. It's very easy to make models. It's very easy. Unfortunately, none of them is actually used, except ours, because we use ours. And it's actually an LLM. It's as simple as that. We convert the crystal structure into a string, and as soon as it's a string, you can use standard machine learning, transformer architectures, whatever you want. So in this particular case, we use a Vygoff representation of the crystal structure. So something like this is translated to something like ternary compound, E-hull low, so close to the stability, has three lithium, oxygen, copper in the ratios 1.111, space group 139, and then come codified Vygoff positions of the compounds. The machine learns this, and it learns because we trained it in 5 million compounds, and then it just spews out at the rate of 500,000 a day new crystal structures. Okay? That's how it works. Next step, universal machine learning force fields. So we don't develop them ourselves. We provide the data to train them, so all the new ones are trained on our data. And here's just a small benchmark from ours. These are a series of force fields. This is the first one, magnet, is from 2021. It's like prehistory. This is the best one. It's from Meta. It's called ESN. And this is the scale of errors in a test set that is crosses dimensionality. So it's 0D, molecules, classes, and all that stuff. 1D, nanowires, nanotubes, ribbons. 2D, you know what it is, and bulk. The scale here is from -50 to +50 milli-electron volts per atom. The error of ESN, it's 75% of the times beneath 5 milli-electron volts per atom. This is essentially the precision you have in your VASP calculation. So if you use ESN, it's the same thing as using VASP. It's just 100,000 times faster. Yeah? It's 1 month old. It's already deprecated. Meta no longer supports it. And it's just 1 month old or 2 month old. Now they have a new one. This is just equilibrium properties. This is energy. I can show you volumes or geometries. They're absolutely spot on, amazingly. Let's do something more complicated. These are phonons. This is PB-Sol. So these are PB data and compared with PB-Sol. So the difference in this case of the maximum phonon frequency between a PB and the PB-Sol calculation is this one. So if you want, this gives you error of DFT. Yeah? This is MatterSim. That is the Microsoft force field. You see, the width of this is already smaller than that. Yeah? ESN, we don't have it here, but it's actually already better than MatterSim. So phonons, if you accept an error that is a couple of Kelvin, why should you spend 1 month running a supercomputer? Just do this. It takes 1 minute. Yeah? So that's the state of affairs now. So next, prediction, distance to the convex hull, and prediction to the properties. So we have a series of models for whatever property you want. I mean, whatever you can calculate, you can predict, right? This is some idea, for you to have an idea. So band gaps, so structure, band gap. Error is 30 millieVs. Let's do something, I know, volume per atom. This is a good one. You get 39 milli angstroms cube per atom. So this is fine. Well, energies, this is important. Distance to the convex hull from the structure, we are at 18 milli-electron volts per atom. Yeah? So it all works. Of course, these models were trained with 4 million points. Yeah? That's the point. Not 20, not 7, not 100, not 1,000. It's 4 million points. And you need 4 million points. Otherwise, it doesn't work. Next up, what do we do with all this stuff? So our database. That's what we're talking about. This is the mother of all the models, right? All the models that are here are trained with this. Also, the model of Meta and the model of Microsoft is trained with this. Not only, but also. And then everything that comes out from here ends up there. So just a few numbers about it. So this is database. You can go there. We also have a QR code. It's not very hard to make, right? We have at the moment TFT calculations for around 5.5 million compounds, 5.7 million, whatever. We actually have, most of the data is PBE, like everybody else. I mean, we are addicted to the PBE. The community is addicted. It's very hard to break this addiction. We also have some PBSOL and scan calculations. Scan, not R2 scan, not R4 scan, real scan calculations. They're much less used, and it's much smaller. So we have around 500,000 compounds with PBSOL, 500,000 with scan. Then we started using this universal machine learning force fields to build material databases also, right? So our 3D database done with the universal force field now has 120 million compounds. I can tell you that although we are generating 500,000 compounds a day, the rate that interesting new compounds appears is going down dramatically. We are just getting alloys now. Rare earth alloys, that's basically it, which I read as there are no more compounds. So what is here is what exists. You can dream, let's make a compound, design a compound to do this and that. It's already here. And if it's not here, it doesn't exist. Yeah? And I will show you some examples. There are many properties you cannot optimize. Yeah. Unfortunately, this is the case. If you want a better conventional superconductor than MGB2, you can go to the guys doing string theory and go to one of their alternate universes, because in this one, it doesn't exist. Yeah? We can already do these kind of statements with the data we have. We have an Optimade interface, but I don't really care, because the people who are our users, they just download the data. And our users are Meta and Microsoft and Orbital Materials, and these people, they don't care about these interfaces. They just download the data, and that's it. Then, yeah, we have databases now. We have 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional materials. And it's Creative Commons like it should be. And that's it. So I will show you the evolution of the workflow in the past 3 or 4 years, OK? So when we started doing this, and it was in 2013, I think, we were just trying out everything. So we were doing like a flow was doing, just grab a structure, put all possible chemistries, and just run it. This is the distance to the convex hull, and this here is the distribution of compounds that you get by doing exactly that. So you see, there are very few. We are interested in this point here, 0. These are the stable compounds, or around here. Yeah, you see, this is not very efficient. And then we started updating our machine learning models and whatever. And this is already a recent iteration. It's using the magnet energy to calculate the distance to the convex hull. And then you do the PB calculation and check. And you see, the percentage of compounds close here increased a lot. So this was much better. This means that this is stuff that we don't care, because they will never be made in a lab, right? So it was already much better. But then, again, and the basic point, we have more data. We could train better models. Now we are here. So essentially, 70% of the compounds that the machine predicts that are stable, and the other ones are not far. So this is something that Google also did with their GNOME database. They were saying that at the end, after training all these things, most of the compounds that were predicted by the machine to be stable were stable. Yeah? And this is what we see. You just need 4 or 5 million points, and that's everything works. And it doesn't matter which model you use, literally. For as long as the model is scalable, this means you can put as many parameters as you want. If you have enough data, it will work. You don't have to be smart. Actually, that's one of the lessons you learn in machine learning. Don't be smart. Just put more data, and don't be smart. Because the machine is smarter than you. Than me, certainly. You, I don't know, but with me, certainly. Just a few more numbers. So this is the rate of insertion of the DFT calculations in the database. So we started in 2013. Now, at the beginning, it was very fast because we were doing what many people were doing. So, running cubic compounds with very few atoms in the unit cell, and it goes very fast. Yeah. So that's the bump here. It was perovskites, Oystlers, and half-Oyster compounds that are really so simple that it's embarrassing. And then it was harder because the compounds became harder. And now we got, in 2021 or so, we started using real supercomputers. And it went up a lot. And not only that, but the quality of the compounds we're calculating is higher, because the pre-selection done by the machine learning is much better. So now you see we are at around 1 million something compounds a year. These are the other tables. So I put here we have 2D tables. We started doing calculations under pressure. So we have already a pretty good table for mantle pressures. So because that's something that is much more unknown than ambient pressure, but we're doing it. I think it will take us another year or so, and we'll have the pressure data at the state that is, we will have basically the phase diagram of the mantle by 1 year time or so. For you to see also comparing the scale of things, this is the distance to the convex hull of our PBE database that has 5 million compounds, and this is our machine learning database. So the scale here is millions. Okay, so on the convex hull, we have, or very close to it, there are around 2 million compounds in this orbital database. And really, there's not much difference in terms of quality of calculation from this force field to DFT. When I grab one of these structures and I do a DFT calculation, often it does 3 geometry optimization steps. And the energy changes by 2 millieV per atom. So we do it because the community will never believe this, because it's moreover from a company, but it's really not necessary anymore. That's my point of view. And now why do we want to do this? Let's go back to the beginning. And this is the last part. I told you, now we have all compounds. We can calculate distributions of properties. And let's do a couple of exercises. So this is the volumetric mass density. So the weight divided by the volume. Yeah. And this is the distribution we have. So now let's make a quiz. What is the highest density compound that exists or that can exist on Earth? Who knows? You learned about volumetric mass density, I think, in the primary school, right? Or at the beginning of high school. So what is the material that exists on Earth that has the highest density?
Tungsten?
It's not tungsten. Next try.
Uranium?
We are close. It's plutonium. Of course, plutonium is not really the solution we want. So osmium, who said osmium? Osmium. Actually, it's not technically osmium. It's ordered compounds of osmium with iridium. But osmium is very close. This is the compound we have that has the highest density. Osmium is either osmium or iridium, depending on the conditions, can be one or the other, actually. Low density. What is the lowest density material? Solid. Let's not cheat. What is the lowest density material that exists?
Boron.
Boron?
Yeah.
No. No. You need empty space. Sorry? If I make grab cardboard and make something like this, it will be less dense than any material in existence, right? But let's keep it inorganic bulk compounds. Let's not, it's actually magnesium boron hydrate. This is the compound. So these are experimental compounds, moreover. Huh? This was very much studied in the context of hydrogen storage. And there are many, many phases, and they have lots of holes. So let's do something that's a little bit more complicated. Work of last week, for you to see what one can do in 1 week of work now. Electrical conductivity. So it's hard to calculate electrical conductivity. So here there is just, I will not go through the whole story, but let's put like that. In this axis is the electronic part, higher, the best. Here is the electron phonon coupling that is the primary scattering mechanism in ordered metals. So you want to have small electron photon scattering. You want to have high electric part of the conductivity. And this is what you get. Silver. You will probably never find anything that conducts electricity better than silver, regardless of how many years you will start searching. It simply will not exist. And then you see what are the outliers: copper, gold, and aluminum. These things here, it's brass. And we have every kind of compounds that you can imagine, but if you want to have a good electrical conductor, it doesn't matter that you have quinquenary compounds with very complicated unit cells. Doesn't matter, because the solution is silver. And this is a bit depressing, and we have been finding this over and over and over again, that for some properties, yeah, we can just quit. Most properties. Anyway, I'm very pessimistic. Conclusion. Machine learning has accelerated significantly our workflows. It's a revolution, believe it or not. We can do things orders of magnitude faster than 5 years ago. We can study all compounds in existence in 1 week, sometimes. Most relevant compounds are already in our database and in the database of Google that is closed. So these two databases already include essentially all inorganic ordered compounds that will ever exist. Believe it or not, that's how it goes. Large parts of material space have already been scanned for many properties. I mean, people are not sitting down just with the data, they use it. Now, what we need? Well, we'll keep on exploring the entire chemical space. We will go into alloys, but that's fine, they're also important. We have to improve accuracy. We have to move beyond the PBE. PBE is by far not the best functional. It's much better than most people think. So, quiz, what is the error of the PBE in calculating formation energy? Who knows? Everybody here, or half the people here, use the PBE, I bet, except the experimentalists. What is the error of the PBE in calculating information energy? 50%. 50%. It's actually horrible. It's around 230 millieV per atom, because the PBE describes very badly the elementary substances that are much harder. So it's not really a useful number. And the reaction energy, the ones that matter, anybody knows? It's around 75 millielectron volts per atom. So it's slightly worse than chemical accuracy, but it's not as bad as most people think. But we have to move beyond that. And I think academia will be completely rolled over by the big companies again. You will see in around 3 weeks' time, just pay attention to your feed. You will see that big companies do things a bit faster and better than small academic groups. Anyway, we have to include thermodynamics. That's the big problem. Materials are not stoichiometric in many cases. They are not nice and pretty. We have to include temperature. We have to include disorder, at least. We have to include the microstructure. We have to include all these line defects, all these boundaries, everything. We have to include external electric and magnetic fields. This is a technical problem. It's not a fundamental problem. All these things are technical problems. There is no fundamental problem anymore to be solved in this field. It's just technical. You need data. You don't need anything else. You just need data. Okay? This is all. And thank you for your attention. I hope I was not too unpolite.